Hi guys, welcome to Learn Electronics Repair. I have a ATX power supply here, or if you like a micro ATX. It's one of the physically smaller ones. It's not the one from this box. I had a customer who brought an all-in-one computer in, which is what this was taken from, and he needed it urgently so he could get his New Year's Eve radio show done, basically. So I ordered him a replacement one, which was this. I fitted it in the all-in-one, it's now working, and I have the faulty one. I thought it might be a nice idea to look at this. I've not done any power supply repair for a little while. When it was in the all-in-one, it was just completely dead. It didn't switch on at all. So let's have a look and see what the problem is with this. I'll attach it to my analyzer. I've modified this analyzer. I'll link the video from this one in the description and at the end if I remember to do it. Yeah. So normally with these, if there's no supply on the 12 volt rail, it won't even switch on, which is not much use if you have a power supply, for example, that doesn't have any 5 volt standby. Although without any 5 volt standby, it shouldn't switch on, but never mind. I've actually modified it so that if any voltage rail is present, even the 3.3, the standby, the 5 volts, the 12, whatever is present, this will switch on. So let's have a look. I know this isn't going to go bang or anything like that because it didn't when it was in the all-in-one, but I'll put the light bulb limiter in series. It's very useful to do this because when I power this up, if the light bulb comes on dim and goes off, I know that some power is actually getting into here, and probably the main capacitors are charged. So we'll use the light bulb for that reason. You can see it underneath here, and I will just check this is set to limit. So let's see what the light bulb does when we switch this on. Well, it flashed once and went off. So that tells me that there is power getting into the power supply. It also tells me the capacitors are probably charged up because nothing happened. Yeah, this didn't do anything at all. So let's open it up, taking some precautions because of the large electrolytic capacitor, maybe high voltage inside it. And let's have a look to see what the problem is. Okay, I have the top taken off it. The first thing I need to do is to make sure there's no voltage in this capacitor. Can I find a way to do that without taking the PCB out? Not easily, okay, not easily. I can see the bridge rectifier, which is tucked down behind here, but that isn't easy to get to either. So with this one, I think I'm either going to have to just leave it for a while and hopefully the capacitor will discharge, or I just need to be very careful with it. Because there's no way to be sure if there is any high voltage in the capacitor, I've left it a little while. To get this apart, I'm going to unsolder these two wires. These are on the AC side of the bridge rectifier, so even if there is charge in this capacitor, there won't be any voltage here. So we'll just take these off and then we should be able to undo the screws and get inside this. This might be quite difficult to dismantle because it looks like I probably need to take this main socket out. It's probably held in with little clips, top and bottom, and I can't get to the bottom ones. Let's see if we can just actually get this out. Okay. Not easily, that's for sure. So I'm going to have to try and lift this out this way. Now this heatsink will not have any voltage on this, on the low voltage side. The other one may have. It looks like I also need to get this out. So this is like the plastic collar around here. and it doesn't want to come out easily. Okay, it has come out. A little bit of persuasion. It's out. Okay, so now we can hopefully get this out. Okay, I'll try and keep the capacitor away from the metalwork. Something else holding this. No, it looks like it will come out this way. Okay, I have it. I really don't think there's any charge in this thing by now, but I'm being a bit careful if I can. Worst comes to worst, I'll just short it off against the metal case. So if we can just, yeah, disconnect the fan. Now can we get this out? I'm doing this one-handed, you notice. That's the best way to be if you think there's some high voltages present. Okay, I now have the PCB upside down. These are the terminals of the capacitor, and we can check volts range. Is there any voltage in it? Okay. .46 volts. So you can see, even after some time, there is some voltage in the capacitor. 45 volts, 44 volts. See, it's dropping with my meter on it. So that goes to show you guys, the voltage can stay in there for quite some time. The voltage is dropping away now, 30 odd volts. I normally discharge these with a fairly high value power resistor, 2.7k. I've rearranged my bench slightly, and it seems we've gone able since I last used it. But even with the meter on there just drawing a bit of current, it is discharging. To be quite honest, it's getting down to a safe voltage now. I can probably just short the capacitor, might get a little bit of a spark, but that's not a good thing to do with capacitors, to be honest. It's bad for the capacitor, bad for your tools. It's now down to 22 volts anyway, so I will just short it out. Little spark, you saw it. Not much charge left in it though. Don't do that with a capacitor with a lot of voltage in it. Okay. There, the voltage is gone. So we can work on this now. The fact that we had a high voltage in the main capacitor and it wasn't discharging tells me that the main power supply, and for that matter the standby power supply, are not running. But we really knew that anyway because of the fact we had no standby voltage. I'll just clean a bit of dust off it. So with these power supplies, you can see with this one, and I will just zoom down a little bit to show you clearly. These often have 3 transformers. This one has 2. This is the main transformer, so the MOSFET or MOSFETs, which will be here, probably one MOSFET on this one, is driving this transformer. There are 2 devices. No, in fact, that's the bridge rectifier. There are 2 MOSFETs, maybe there are 2 that are driving that. This small transformer with this diode, which is close to this purple wire, this will be the standby power supply. And if there's a third one, it's because the controller IC for the main transistors on the low voltage side, and it uses the transformer to drive the base of the transistors basically from the controller. This has 1, 2, 3 opto isolators. This one I'm fairly confident will be the feedback for the standby supply to maintain the 5 volts. One of these will probably be feedback from the main supply, usually on the 3.3, to monitor the output, and the other one may be used to switch the main controller IC on. So effectively, when you send the signal back on the green wire, something on this side sends a signal via this to a controller of some sort on this side, which then basically drives the main transformer and the main voltages. So that's what I think we have. For this to work, there's a fuse. So let's have a look at the fuse, but I'm fairly sure that will be intact because the light bulb flashed once and we end up with a high voltage of the capacitor, and that's where the fuse normally is, between the mains in and the bridge rectifier, which goes to that. So I think we can say, but we will check it, the fuse will be okay. We need to find the chip that drives the standby, and it's probably this one. Here is the fuse then, and that is fine. I was sure it would be. This chip probably does drive this transformer, and the quickest way to find out is if one of the pins connects to the primary, basically. So we can look from underneath, and we can see straight away, in actual fact, that this is the transformer primary, this is the chip, and these two pins go to this end and these two pins go to this end. So we know that controller chip drives the transformer. This is the secondary of the standby transformer there, and we can see from this side this goes to the diode, which is there, and this is the smoothing capacitor, and this is your 5-volt standby on the purple wire. So why isn't the standby supply running? Well, there's a few possibilities for that. One possibility is that we have a short circuit on the output, but if we did, then this would be running to a short circuit and it would be draining the main capacitor, so it wouldn't hold up charge like it did. So it seems very unlikely we have a short on the output, and we can check that again. I'm on ohms range. Let's have a look across the capacitor, and we don't have a short. Okay, there's no short on the output. We can check the diode. Easiest just to do it in diode mode. Let's see if we have a shorted diode. No, it's reading climbing. Let's try the other way. Is this the diode junction? Yeah, that's the diode junction, and 177 tells me this is a Schottky diode, and that's what you would normally find in there. So I'm confident the diode's okay. There's another chip here. This is probably the one that gets the signal from the green wire and sends that signal via another one of the opto isolators to this side. Yeah, that's probably what that is. There's another chip down here also, and this is probably the one that receives the signal from that one and then drives the main MOSFETs or bipolar transistors that drive the power supply. So that looks likely, yeah. We're interested in this one. We seem to have no standby, so let's have a look to see what this chip is. I may have to use the microscope, but the overhead camera is pretty good. Let's see. So we have F10778 and then OB232FAP. I'm pretty sure the OB is actually the part number, so let's have a look for this one, OB232FAP. Unfortunately, I can't find a datasheet for this actual chip. I can find similar ones, but it really isn't that important even without a datasheet. We should be able to fix this, or at least diagnose where the problem is, because most of these type of power supplies are very similar. They all work in the same way, and if we understand how they work, we can quite easily identify the various parts of the circuit, and we know where to measure voltages and what we expect to find. So then we need to understand these circuits. This is how they work. We have a positive voltage supply. This is coming from the large capacitor, the one that holds the nasty charge inside it. And usually this is about 320 volts on a 220 volt mains. Feeding into this is your bridge rectifier, which converts the AC to DC. But we want to look at this little standby supply. So what we will have is a transformer, primary, connected one end of it to the high positive voltage. This is hot ground. We can call it 0 volts. But as I explained, it ain't 0 to your finger. It's our reference point. This is where we put the black read of our meter. And this goes to the chip. Now, the chip, these invariably are 8-pin chips. Okay. The other end of the chip will go to ground, sometimes through a low value current sensing resistor, sometimes directly. If the resistor is here, this will be low value, less than 1 ohm. Sometimes maybe 1/10 of an ohm or something like that. Now, often you will find that this 8-pin chip actually is a 7-pin chip. So what you'll actually have is 4 pins on one side, 3 pins here. So, drawn it wrong. Let's do it again. 4 pins on this side, 2 pins here, then no pin, then a pin. So effectively there's a pin missing there. If you see that, this is the high voltage pin. This is this one that connects to the primary of the transformer coil and then to the high voltage. The reason for the gap there is just to stop arcing over the high voltage, because when this switches off, there is a high back EMF that comes from this coil, and it causes a high voltage to appear here. So that's why they sometimes are made with a pin missing. You'll see that. Ours has 8 pins on it. The other way you'll commonly find them is that these 2 pins are connected together on the board, and these 2 pins are connected together. And if we look at ours, okay, you can see we have 2 pins here going to the transformer coil, and we have 2 more pins here going to the transformer coil. So you can see that. Now, this is the primary. There's something else you will find there, and that is a reverse biased diode. So the diode goes this way and it connects to the positive. The idea of this diode is called a flyback diode, is that when this switches off and the magnetic field collapses, it gives the voltage somewhere to go. It goes back through this way. So this becomes forward biased, this end more positive than this end when the field collapses. Sometimes that goes directly back to here, but quite often it will go through what's called a snubber network, which is a high value resistor and a high voltage capacitor. Like that, okay? This will usually be several hundreds of kilo ohms, something like that. So that's how the primary of the circuit works. You will have the secondary. This will have a diode, usually, in fact, almost pretty much a Schottky diode, 1 or more capacitors, maybe also an inductor before or after the capacitor, maybe something like that with more capacitors. And that is your out, your volts out. 5 volt, 12 volt, whatever the supply is, and this of safety ground. So you'll have that, okay? You will have coming into this chip on 1 pin, I don't know which one it's going to be, a supply from here. So this is a high value resistor. Sometimes there's more than one of them in series, and this will supply power to the chip. I'll put it here, but it doesn't have to be on pin 1. This is VCC, okay? This is power to this chip. From here, you will find a electrolytic capacitor to hot ground. This is a small capacitor. This is the large one. This one's a small one, but it's an electrolytic. And it will be maybe 10s or 100 microfarads, 50 microfarads, something like that. So up 10 to 100 microfarads, and usually 25, 35 volts, something like that, okay? You'll find that. So the idea of this circuit is that when you apply power, these high value resistors, high, typically 1 meg, 2 meg, maybe several 500 or 680k in series, that sort of thing, yeah. This one here will be several hundred, 100,000 ohms, 100k, I don't know, something like 470k, something like that, 270k, somewhere in that region maybe. So, as I was saying, when you apply power, these high value resistors will charge this capacitor, and it charges up. The time it takes to charge depends on the value of the capacitor, the value of the resistors. It might take a second or two, something like that. And when the voltage here on VCC gets high enough, so this is volts, current. When the voltage on VCC gets high enough, this chip will turn on and start drawing power and start to drive the transformer coil. Inside here is basically a MOSFET and a controller, okay? So this starts pulsing, pulling pulses of currents into here, starts the magnetizing, demagnetizing, and that generates the output. So that's how the chip starts up. Now, the way the circuit works, these resistors are such a high value that once the chip starts running and drawing power, these can't charge the capacitor fast enough to keep it running. It's drawing more current than these can provide. So the supply voltage, let's say it went up to 15 volts and it turned on, the supply voltage will start to drop, okay? And if it drops down to say 9 volts, it will switch off again. That will then, depending on design, either stay switched off, or it will switch, or this will start to charge back up again, and it will switch on again. Okay, some of them switch on again up to 15 volts. You start running again, and this will start to discharge. And if it drops back down to 9, say, it'll stop again. Okay, this is called hysteresis or hysteresis. Hysteresis. I think I spelt it right. Okay. And the idea of this is that something else needs to happen to keep this running. And what needs to happen is this. There'll be another winding on the transformer coil. One end of this will go to hot ground. This ground. And the other end will feed a diode. Okay? Sometimes with a resistor in series, sometimes not. And that, let's call this X, goes back to this chip here. Comes back in here, X. So what's supposed to happen is, when the chip starts running, it generates voltage here through this diode. Sometimes there's another capacitor here. The circuit can vary a little bit. This will provide voltage back to here and continue to charge this capacitor. What happens now when it switches on and this starts drawing current? Because it has this supply, it no longer discharges the capacitor. So now the voltage will come up, and when it reaches 15 volts, for example, that's quite typical, it will start to run. This will generate current. The voltage will drop a little bit while this gets going, and that will come back up and it'll stay. And now this chip can run continually. So that's how this works. There's a few variants. Sometimes you find a Zener diode here. Maybe a 15 volt Zener, 16 volt Zener. It's just to stop the voltage here going too high. Sometimes you will find another capacitor here, as I mentioned there, another small electrolytic, but that's the basic circuit that we have. We also have feedback. We have the opto isolator, which feeds a signal back to here, but that only comes into play when the thing is running. And the situation we have is the power supply is not running. It's either not starting or it's doing this. Okay. So for now, we don't need to worry or take any interest in the feedback circuit. We only need to know about that if basically the output voltage is wrong. Let's have a look then. So we should be able to, even without a data sheet, find all these parts on our PCB because we know what we're looking for. Here then is our chip. This is pin 1. This side is nearest the transformer, and we can see that we have 2 pins connected together and 2 pins connected together. So this basically is the primary side of the transformer. This is where the switch is. Now, one end of the switch here will go to ground, or will go to ground via a low value resistor. So we can have a look. So one end of this, these will go to ground, and ground is the negative end of this big capacitor, which is here. So let's find the ground. Is it this end? Yes. And there's no short from this end, as you'd expect. So that point there is here, and there's no resistor on ours, or it's such a low value it reads like 0. So the transformer coil from here, well, that reads continuity to there. That also reads to there. Okay, but not to there. And this is reading like 0.1 of an ohm. I'll put it into ohms range, it'll probably read a little bit clearer. Yeah. Ouch. Yes, that's like 2.8 ohms. That's the primary side, okay? This end we know is connected to ground. Now, if we also look, this secondary, which feeds this diode, will also be connected to ground. So here's the ground. We know it goes to there. We know it goes to there. Yeah, it reads 0.5 of an ohm. 0.5 of an ohm. This is such a low resistance we can't really see it. 0.3. 0.5, yes. It's reading about 0.2 of an ohm, that actual winding is. And that is effectively that secondary. The other end of the winding, the primary, is up here, 2.8 ohms, and this must go to the positive supply, the positive end of the big capacitor, which we can see is here, which is there. So that will go just off the shot slightly, but I am on it. That will go to this winding, 2.9 ohms. This will be it, 0.4. So we found this winding, we found this winding, okay? And we know the chip connects from here to ground. So we know all that's there. Let's have a look for this diode and if this little network exists. So the way to find that is from the positive line going in. We know it connects to here. Where else does it connect to? And can we find also these resistors? Yeah, can we find these? Can we find these? Let's have a look. So, other side. Well, that is, I think, a high value resistor. There's a yellow stripe there, like 100 kilo ohms or something. And there's a high voltage capacitor next to it. And there's a diode here, yeah? That looks very much like this circuit. Let's have a look. Well, we know this is the positive supply coming in. This one. We can see we found our resistor, 100k. kind of what I said, a bit less than that, but in the hundreds of kilo ohms. We found the capacitor and we found the diode. So from this end of the two, we can see it goes to the diode. This is the 100k resistor, 99k, that reads good. And this is the diode, which comes back to the other end of the winding there. And we can test that diode. Okay, diode mode. Let's test the diode here. It's reading good. Okay, so that's okay. So we found all that. Where are these? Well, there's two more resistors here. It looks like they're connected in series. So this end of this one goes to this end of this one. Yes, so we have two high value resistance series, and these are very high value. That is red, black, blue. That is 20 mega ohms. That is high. And this one's reading 30. If it reads higher than it should, it suggests there's a problem with the resistor. 30 meg. What this one? 22. 30. It looks like that's gone high. I mean, resistors, if they fail, unless they burn up, and even if they do burn up, they will go high or open circuit. I'm pretty sure these are the right resistors, and the reason being, this end here will go to the, to there, and to the high voltage capacitor, which is all on the positive supply rail. So it looks like that one is reading too high, or one of the two is reading too high. That would stop this from starting. So we need to lift one end of these and just check them. The other thing that would stop it from starting is if there's a resistance from here to ground is too low. This capacitor is leaky, for example. Can we find that capacitor? Well, there's one there. Oh, look, and there's a diode here. Yeah, coming from the other winding. Can we see it? We can now see this part of the circuit. Looks like that resistor isn't there. They're not always. And that's connecting to this chip. We can probably see where. Let's have a look. So this is our 320 volts, goes to the first resistor. Okay. Goes to the second resistor. So that must be the power pin, the VCC on the chip. About 20, just reading 30 meg is too much. This will connect, I suspect, to the capacitor. Actually, it doesn't. While we're here then, if that's the capacitor and that's the diode, this one, we may as well test this diode as well. Go to diode mode. Let's see. Almost certainly goes this way. Yeah. 0.54, that's a good diode junction. And we should be able to see it from this side. So this end of the capacitor is on hot ground. Okay. And this end of the capacitor, if we trace from the secondary winding, yep, we can see the diode junction. So all that circuit is okay. This end of the capacitor then must go to one of the pins on the chip, and that will be VCC. Okay. That one. Okay. So we know now this is VCC, and we can measure the voltage on here to see what's happening. The other thing then is the high value resistors should also connect to here. Let's have a look. So we have the 220 meg, which seems to be very high to me, probably too high, and the reading extremely high. Does one end of one of the resistors connect back to this pin? Not that end. Not that end. Okay. Not that end. No, they don't. So this doesn't exactly match the circuit, by I do know why, and I will explain to you why. What I would like to test now is the resistors from here to ground. For example, is that capacitor leaking? Because that will stop it from starting. So hot ground. Okay, capacitor. It actually reads open circuit, you would expect it to be. Okay, and of interest from here, the capacitor to the supply. Okay, that reads like 5 mega ohms. That's more like the value of startup I would expect to find, not 40. So these two, I'm not sure exactly what they're doing, but I don't think they're part of the startup. What I think we have here is a variance, and this is also common. So you need to be aware of this. Sometimes you'll have this circuit whereby if this is the pin, VCC is being fed from the secondary of the transformer. Like we've just described. Okay. But there's no high value resistors here to get it started, because obviously it needs to get starting before this can provide power. It needs something to start it. Yeah, sometimes actually the MOSFET internally effectively has built into it, or built into the chip, a high value resistor internally, which goes from here to here, internally in the chip. Yeah, so if you can't find these, you'll probably find it's in the chip, and ours seems to be reading about 5 meg. So all the readings seem to be sort of okay. To figure out what's going on, we need to look at VCC when we power up, and to see, do we get any voltage here? Is it enough to start the chip? If it isn't, let's change this capacitor. That's the first thing. Yeah, if it is enough to start the chip, is it doing this oscillating thing? Is it stopping and starting? If it's stopping and starting, it's because there's something wrong with this circuit feeding the voltage back, or there's something wrong on the secondary, too much load. But we know we don't have any shorts here. Let's measure the voltage then on VCC and see what we can work out from that. I've attached the mains leads. This is just an IEC connector I keep with a couple of crocodile clips on. I find it a convenient way to attach power to things like this. If you like, you could solder wires, you could put some heat shrink on, you could make it insulated. I have my light bulb in circuit, so if these accidentally touch, the worst thing that will happen is the light bulb will come on. And we can measure the voltage. Now, if you're not comfortable working with high voltages, you can solder short wires on here. You can hold your probes on them. Personally, I like to attach one probe to hot ground with a crocodile lead, and then I just have one and I'm probing with one hand. This is a very good practice, because it means if you get an electric shock, it's not going to go up one arm across your chest and down the other arm, which is about the worst thing that could happen to you with electricity. So let's also attach a lead on here. If you're happy to hold both probes, that really just means you're becoming complacent with electricity, and that's actually quite a dangerous thing to do. But at the end of the day, it is your personal choice. Okay. Sometimes I do it. You've no doubt seen me do it before now, but this is a relatively safe way to work. So meter on, volts DC, electricity on, yeah? Now we will have, this is your main capacitor. This will have a lot of voltage in it, 320 volts, yeah? What we want to know is what's here. 4.28. That is not enough voltage to start one of these chips. I'll switch this off, and this is the danger with this. The power's now off, yeah? And you see the voltage, it's going away slowly. It will take a long time for that voltage to become safe where you will not get a very nasty shock if you touch it. Yeah, so that's why you need to be a bit cautious with this. This still is maintaining 4.26 volts. What's happening on the output of it? Well, obviously, so this is connected to there basically. This is also connected to there. So this MOSFET in here is off. It's not doing anything. This is the hot ground end. So it looks to me like this chip doesn't have enough startup power. It could be a problem with this capacitor. We need to change that. If not, then we can have a look at this high value resistor, this 20 meg that reads more, but I'm not totally convinced that is part of the circuit. Although having said that, I don't know what else it would be doing. But before we do anything at all, we need to wait for that to go away. Either by connecting the power resistor across the capacitor or waiting. It looks then like this chip doesn't have enough power to run. We can see this is the diode which we trace through. It comes from the secondary on here, goes to the capacitor, and from the diode, if I go to this chip, well, that reads 0, and that reads to a diode. Okay, so the one that's reading 0 will be the end of the diode that's connected to the secondary winding, and that goes to ground. So effectively that pin on the chip is ground, and the other one reads to a diode junction. So that's the diode is good, we know it's good. This is the other end of the diode, the capacitor. So this is a supply rail. This is the one that is powered from the secondary on here. The one that starts it, I can only see, unless it's internal, which it could be, is coming through these two high value resistors, and that goes to pin 1 here. And we know, because we looked at it before, these 20 meg resistors don't read right. Okay, that's actually reading open. That's reading 20, that's reading about correct. And this one actually reads open circuit. Yeah. So it looks like that resistor's failed. That would mean there's not enough startup voltage. The other likely possibility is this capacitor is leaking, and it's not leaking to the multimeter. We go from the pin here to ground. It reads, well, there's a bit of charge in the capacitor actually. That's probably come from the test meter itself, and it reads well into the mega ohm. So I doubt that's leaking, but it could do under voltage. But the one thing for certain is this resistor was reading like about 30 meg or something. Now it's reading open. So let's take that resistor out. Let's check it. And it should be faulty, because really there's nothing that can happen in a circuit to make a resistor read higher than it should do. No matter what's connected to it, what's in parallel with it, if you read across the resistor and it reads higher than it should do, you've got a problem with the resistor. Let's unsolder it. I've removed the resistor. We can check this one again in the circuit. Now it's open circuit effectively at one end, the other one's removed. This should read 20. Yeah. And it reads 20. The other one, let's check it. Now with a high value resistor like this, by the way, you can't hold both probes with your fingers like so, because you can see on the multimeter your skin has a resistance. You can hold one end, but the other end you need to touch with the probe. And that's reading open circuit. So this is red, black, blue, which is a 20 mega ohm resistor, a very high value. The highest value I actually have is 10. I can order some of these. If I ever find something like this faulty, I will go and order some, because if I found one once, I'll find one again sometime. But what I can do for now is use two 10 meg resistors in series, and let's see if it works. These are 10 meg resistors. Just solder them together. I won't do it over the board so I don't drop any solder onto it. That was a bit of a bad idea. Let's do it this way. So we now have a 20 meg resistor, and hopefully it's not too hot to pick up. We can check that. So we can again just hold one end of our finger, touch the other end, and that's reading 20 mega ohms. Alright, let's fit this. Okay, there are our two resistors in circuit. First one, 20, second one, 20. Now in most instances I would probably just try this and then clean the flux up, but because this is a high voltage circuit, 320 volts on one end of these resistors, probably when it's working 10 or 15 volts on the other end, not 5. And because the resistors are very high value, I will clean this up. I don't think this flux is conductive at all, but this is the time where you should make sure you clean it. Okay, that's nice and clean. I'm just going to bend this leg a little bit further away from there, so there isn't too narrow a gap and it doesn't arc over. I mean, that leg there, I haven't unsoldered it. That's how it was originally, but since I've spotted it, I think I'll do that with it. Now, let's see if this works. I've attached the ATX tester, so if any voltage comes on, this will show it, even if it's just a standby. Make sure these wires are nowhere near to each other. I have the light bulb in series, a current limiter. Let's see what this does. Well, that's what it does. So we have 5 volts standby, but the rest of the voltage are reading low. This looks like we fixed one part of the problem, and we now have some other problem. It could be that having the light bulb current limiter in series is slowing the way this is powering up maybe, and the main power supply isn't starting. I know it's not going to blow up, so let's switch the current limiter off and now see what it does. Yeah, and we now have the voltages. The only reason it's bleeping now is because I don't have the 4-pin connector attached, which is this one, so we can attach this. 4-pin, and now it should power up and not bleep. Okay, and there we have all the voltages nice and stable, so that one is repaired. Well guys, I hope you enjoyed that one. A success, and I hope I explained that well enough so that you can work in similar situations if you have to, where you have no data sheet, just by understanding the basic layout of these circuits, because they're all basically the same. I'd just like to say then, a happy new year to all of you. It is January the 1st today. I'm awake. I don't have too much of a headache from last night. And I've just popped into the office for a very short time to finish this video. I'd finished most of it yesterday. You'll notice the t-shirts changed colour. So I just want to say then, a happy new year to all of you. I hope it's a prosperous one. I hope you learn a lot more about electronics and electronic repair. And I will see you all soon. Ciao for now, guys.